All right, so in this session, we will discuss oracles, particularly a general design of oracles that you can use to build oracles with required functionality. And our focus would be on phase oracles because these are the one which are most commonly used in quantum computing. But you can use the same method for other types of oracles as well. And particularly our focus would be on oracles for Grover search algorithm. And then we will go on to implement these oracles in Qiskit. Before we begin, I will just, have one word of caution. The way I'm going to present it, I will not worry about optimality in terms of number of gates, because the same function you can implement using different number of gates, right? And even though since nowadays our quantum computers have very few qubits and the coherence time is not very long, we would like ideally to have an oracle that implements the given function using the smallest number of gates, and so that the depth and width of the circuit is not great. But in this presentation, I will not worry about that. My idea would be to give you a principle that you can use to actually build any oracle that you want very easily. And of course, this is still an open question, how to come up with an optimal oracle for a given problem. But that's something that we will not worry about in this session. So let me start sharing my screen, and then we will discuss this thing. Okay, so let's go to full screen. All right, so oracles, if I go back again, there are devices like this. So if you have a black box, with certain number of inputs, which implements some function f of x, which goes to 1-bit output. So for example, there is an f of x, which takes an n-bit string input, but gives at output either 0 and 1. So there could be a lot of functions that you can, define in this way. And or the starting point of oracle is implementation of this function. Most of the time, we are interested in oracles of two types. So you can say, and before I go there, you can see from here that even if you are somehow able to create a circuit that quantum mechanically implements this black box, this cannot be used in quantum computing, because in quantum computing, we require all processing to be unitary, which means, first of all, that the number of inputs and number of outputs have to be the same. And then the evolution have to be, under a unitary transformation. So this thing, in itself is not a quantum mechanical, computing part, because this goes from many inputs to a single output. So that's why we have to come up with a way of, preserving the unitarity, so that the number of inputs and number of outputs are the same. So one way of doing is this, that this input that goes to this function f of x. So this is n-bit long. So let's say the bit string at the input or the state is xcat. So we, can have an oracle, let's say OF, which works like this, that maybe there's an input here. Let's call it some B state. And then all of this input is presented at the output again. And this, in general, we can have many auxiliary inputs over here, but let's actually do that. So if we have m input, m-bit long input here, and there's an input state B. So we have an m-bit output over here, and let's say this gives us a state like this. So this is the function f appears, in something in this part. Usually in most of our oracle, this m is equal to 1. So there's one bit, input, which is XORed with this function f of x, which is being implemented inside this oracle. And since we can set b in any way we want, if let's say b is 0, then this output is just f of x, because if b is 0, if f is 1, 1 plus 0 is 1. If b is 0, f is 0, 0 plus 0 is 0. So this is essentially f of x. So you can call it, an amplitude oracle or a bit oracle or just an oracle. The other possibility is that, so let's call it amplitude oracle, just to differentiate it from phase oracle. Because this phase oracle works if we set this b to this minus state, which is nothing but 1 over square root 2, 0, minus 1. And this b plus f of x, where f of x is a single bit, either 0 or 1, will be equal to minus if f is 0. Because if this is 0, then whatever b is, where in this case b is a negative state, we get negative. But if f is 1, then 0 plus 1 would be 1, and 1 plus 0 would be 0 plus 1 would be 1, and 1 plus 1 would be 0. So we can take minus common, and this becomes this state. So this is like equivalent to saying that this function f of x appears in the phase of this minus 1 term, where this, this is minus. So this minus state, which is being inputted here, is being, given a phase term minus 1 power f of x. And if we talk about, the total state of this oracle, then we can think of this, phase term either with this bit or with the input x. So this is the, general construction of these oracles. By the way, in addition to this bit, which we usually call, ancilia bit, which is either set to 0 or minus 1 to make it an amplitude or a phase oracle. And there is, this n bit long x input and n bit long x output. There might be other bits, which we can call ancillary bits, which you can picture as being part of, this process, or maybe separate. So they also start in the same state, let's say some m state, and they may go on in m state. So they remain the same at the input and output. And usually they are just used for the purpose of, making an oracle, and then there's no use for them later on. Anyhow, so in general, if b is equal to minus state, then this oracle is called the phase oracle. So far, we have only used a phase oracle, but next week in Simon's algorithm, we will also use an amplitude oracle. Okay, so let's now come to building these oracles. So oracles essentially implements, so actually I will just restrict myself to phase oracles. So phase oracles are like this, that if the state, input state is minus an x, which is transformed to minus 1 power f of x minus x. And if we are just working with, these x qubits, so we can essentially, this minus is here and minus is here, we can essentially picture it to be like this, that x state is form to -1 power f of x. So which essentially means that to implement this thing, we have to implement the x gates and this, ancilia qubit according to this function f of x. So if you have, let's say, a circuit like this, suppose you want a single bit oracle. So for single bit oracle, we can, so our x is just, this input, and this is in minus. So if we want to implement, so if x is just single bit, we can only have, a few types of function. So either f of 0, so let's say if x is just a single bit, then we can have f of x of only a few types. So f of x could be, 0 for all x is equal to 0 or 1. So even if x is 0 or 1, we want an output 0. Or we can have f of x is equal to 1 for all x. So it doesn't matter what, x is, we want to have f of x equal to 1. So this essentially means that x should go to x always. So it means the best oracle for this thing is this x here and this minus here, and that's it. This oracle implements this function because f of x is 0, so there's no phase, and doesn't matter what x 0 or 1. So whether x 0 or 1, it will just go to the output state. For this function that we want f of x to be 1, that we always want a phase irrespective of the fact if x is 1 or 0. So what we can do for this one, that we just put an x gate over here, or equivalently we can just put an x gate over here. So this can implement the second function. However, if our function is like this, that f of x is equal to 0 when x is 0 and it is 1 when x is 1. So it means I don't want any phase if x is 0, and I want phase if x is 1. So this circuit can implement this thing. Because when x is 0, this x gate will not work. When x is 1, this gate will work, and I will get this a flip here, which can be considered, to be present with this state. So this C naught single, Cx gate implements this function f of x is equal to 0 for x0 and f of x1 for x1. What if you, want to implement this function? That's 1 when x is 0 and it is 0 when x is 1. So what we can do, we can put an x gate here, and then a C naught like this. Now you see, when x is 0, this x gate will make it 1, and when this is 1, this will act and I will get a phase. But at the end, this 1 is again being, xed, so we are getting 0 state at the output again. So because we have to make sure that our oracle has the same output state as the input state on these working qubits. So this circuit can also be, represented with this thing. So this, instead of this dot, if you have a hole here, it means this Cx gate essentially works if this control bit is 0 and implements this x gate. If this control bit is 1, then it doesn't work. But this can be implemented using a regular Cx gate like this. And this notation, is very useful whenever we have to do an x, a control operation, and then an x again. So then instead of, showing this x, control, and x, we can just show a hole, which tells us that this the logic over here is reversed with respect to the control bit. Okay, so when you have a single bit as a working qubit, then there are only 4 possibilities for the function f of x, and we have shown how to implement all those 4 functions. So any question regarding this single qubit oracle? If not, let's go on to 2-qubit oracles. And 2-qubit, from number of qubit, I refer to the working qubits. So suppose that we now have 2 qubits acting as control, and then there is, you know, 1 NCDA qubit. And there are several possibilities for the function. If you want your f of x to be 0 for all x, or you want your f of x to be 1 for all x, then it is simple. F of x 0 for all x is just like this. And f of x 1 for all x is essentially just, you know, an x gate over here. And this will implement f of x 1 for all x, because this -1 bit will be flipped. Doesn't matter what the, you know, input is. Okay. But if you have a phase functions like this, that f of x is balanced. Balanced mean that it is 1 for half of the inputs, and it's, you know, 0 for the other half. You can implement it using a combination of C0 gates. For example, you can put a C0 with respect to this, or maybe a whole like this and like this, which, you know, mean that there's an X control and X. So with these types of circuits, you can implement different balanced functions. Even the multiplication with a secret bit string gives a balanced function, because it gives f of x 1 for half of the input and f of x 0 for the other half. So all of these balanced functions can be implemented with oracles like this. Actually, even if you have more than 2 qubits, you can implement you know, balanced oracles using different combinations of control x. And this is something that we have already done. So I'm not giving more examples for this balanced function implementation. So it's clear so far? But let's now discuss the 2-qubit oracles for unbalanced functions. Okay, that let's say I want to have a situation like this, that if the input state is you know, 0 0 0 1 1 0 or 1 1, and let's say I want output something like this, 0 1 1 0 1 1, that is a negative sign appearing only in front of, you know, one output, and all others are positive. And you know, we require this to implement our function uf naught in the Grover oracle, because uf naught was 2 0 0 minus I. So this is actually equal to this thing, but this is equivalent, you know, since this is equivalent to, right, this will essentially do the same work except for the global phase. So if we can implement, you know, an oracle like this, this will also do the same job, because both of these are computationally equivalent. But this one, you know, is easier because I now have to worry about putting a minus sign only in front of one of the input. But you know, we also require an oracle, for example, for UF. UF, you know, was something like this. If you recall, UF was identity minus this W state. where W was our solution state, that this Grover oracle should be able to mark the solutions. If you are, for example, this 0, 1, 0 state is your solution state. This is the index that is the answer to the search problem. Then this should be able to give a negative sign to that problem, to that index, and positive to all other. Or maybe there are two solutions. For example, this is also a solution, so it should be able to give a minus sign in front of that as well. And similarly, if we have a 3-qubit oracle, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So maybe I want to mark only this state and perhaps this state, and all other state should just go there as it is with positive sign. So we need to be able to build oracles for situations like these. So for that, to accomplish these things, let me introduce the Toffoli gate. So let's introduce Toffoli gate. So Toffoli gate is essentially a control X gate. So in Qiskit, it has this symbol CCX, but in books you can also see it written something like C square X and so on. And this is a gate like this. So if you talk about its truth table, it works like this. That if both control qubits are 1, 1, the X is flipped. This is the output. So if this control 1, 0 goes to 1. If this control 1, 1 goes to 0. For all other combinations of input 3-qubit inputs, for example, if this is 0, 1, this is 0, this remains 0, 1. If this is 1, 0, this is 0, this remains 1, 0, 0. If this is 0, 1, this is 1, this remains 0, 1. And you get the idea. So I can write all the remaining 6 combinations, and they're all coming here as it is. So this means that the Toffoli gate, which has a symbol like this, is actually an entangling operation between 3 qubits, because depending on the state of these 2 qubits, you perform an X gate on the 3rd qubit. So C1, C2, and this is your target qubit. And it has a truth table like this, that an X gate is implemented here only if these 2 qubits are in the 1 state, which means if I now use this control X gate to build my 2-qubit oracle, I can think of this as my working qubits X, and think of this as my ancilia qubit. And if I put it in the minus state like this, so this X gate will be performed only when this is 1 and this is 1. So this will then have a truth table like this. So if I now take the C1, C2 as my X state, so if they are 0, 0, they are 0, 0, nothing will happen to this. So my no phase added here. So if they are 0, 1, no phase added here, because 0, 1 doesn't do anything here. So I get 0, 1 again. If they are 1, 0, I get 1, 0 at the output again. But if they're both 1, 1, I get minus 1 at the output, because if they're both 1, 1, an X gate is applied to this qubit, and I can think of that phase present with these 2 outputs. So it means this Toffoli gate can give us a way of putting a minus sign in front of only one of the inputs. And it's very easy to select which input state you want to mark. Because if I put a hole here, unfortunately this eraser erases everything. So let me put a hole here. So now this means that this control gate will be performed only when this is in 1 0 state, because the control is no reverse here. So if it is 1, this is 0. So it means, let's say this is C1, this is C2. So C1 has to be 1 and C2 has to be 0. So it is this state. So minus sign will come in front of this and not in front of this. And this circuit, by the way, this one is nothing but this circuit. Okay, so let's now write them, X. So this is your X naught, this is X1, and this is in minus state. So this hole that you're seeing here, I can implement it with an X gate before and after the second qubit. So using this Toffoli gate, which is directly available in Qiskit, I can implement this phase oracle where I desire a minus sign in front of only, one of the inputs. Is that clear to everyone?
Yes, sir.
Okay, so let me just ask a quick question to, let me see who are the people present here. So let's say the Abdullah Ahmed, can you think of a way that if I have to mark, given minus sign to two of the input, how can I do it using Toffoli gate, not using CX gate? Since this is only 4 combination, when I have to mark 2 of them, I know that you can do using control X. We just discussed it earlier, but can you think of a way of using Toffoli gates to mark 2 of the inputs? No? So you can do it like this. For example, you want to mark this input and this input with a minus sign. So you first think of a circuit for marking this one, and then think of a circuit that marks this one, and then you combine them. For example, you can mark this single element using this circuit. And then you can mark the other element using this circuit. So if I, put these two in series, so the input is coming from here. So this will do its job for one of the input combination, and this will do its job for the other combination. The only comment that I have, that when you are implementing this, when you are designing it on paper, this is fine, but when you are implementing it on computer, you might have to think about if there are any X gates that cancel out, or if you are implementing this Toffoli gate using combination of CX gate, so you might want to cancel out the gates that can be canceled out to get a smaller number of gates. But for for our work that we are doing, we won't be worrying too much about the optimality right now.
Excuse me, sir.
Did he?
Sir, will the order matter here, like for these two holes?
No, it doesn't matter.
Okay.
Let me see if my volume is high enough. Okay, now I have increased the volume. Hopefully this will make the video a bit better. Okay, so let's now come to a 3-qubit oracle. Okay, and naturally I can extend the concept like this. Suppose I somehow have access to this gate. Okay, so this is C1, C2, C3, and this is in minus state, where this gate is, you can call it as C3X, or you can call it CCX, and so on. But this is not available in Qiskit. Okay, you will have to think of its implementation. I'll just talk about it a little bit later. But if I have access to such a gate, you can easily see that this will mark only this state, because all these three have to be 1 before an inversion of this ancilia qubit takes place, which means that negative sign will appear only in front of this state, and all other state will come with a positive sign. And if you want to, mark this state, suppose I want a circuit that marks this state, that it gives a minus sign to this state. So all I have to do is implement this gate. Right? Because this will work on 1, 0, 1. This is just equivalent to, by the way, this gate. X, 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 and control X. So this can be written in terms of C, 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 X like this. But if I have access to this gate, I can now mark this one. And suppose I want a circuit that marks 0, 1, 1, that gives minus sign to this state, and it gives a minus sign to 0, 0, 1 state. And it gives to, positive sign to all other. So what would be the circuit for that? I can combine the circuit for this one and for this one together. So for 0, 1, 1, it would be, let's say this is the first qubit on the top. So this is control, control, and this is opposite. So this will do the job for this part. And for 0, 0, 1, I will have this circuit. So this can, this whole circuit can mark these two elements. And when I was talking about, optimization, I was, talking like this, because this means that these are two control, and this is a whole. So it means there's going to be an X before and after this. And you see, this one is X control X, but this is also control X, X. But this X and this X will be X square, which is identity. So this is nothing but an X control, control, and X. Like this. So this circuit can mark these two elements. So it can implement a phase oracle that gives a minus sign for these two inputs. Is the idea clear? Asif?
Yes, sir.
Okay, now only one thing is left, and that is how to implement this, C cube circuit. Because this is not available in Qiskit. By the way, in Qiskit, CCX is available, but it doesn't mean that Qiskit, implement the IBM hardware is able to do an entangling operation between 3 qubits. It doesn't. So this is not a primitive gate that is available in IBM, but they have. This is almost like a bit high level routine, which has been implemented using a few control X operations and a couple of other, single qubit operation. But let's not worry about that, because this is available to us as a direct, gate that we can invoke. So I will present its design in terms of this Toffoli gate. So this, C cube operation can be done like this. So let's say I have this qubit set in this minus sign, and let me introduce, one auxiliary qubit that I have put into 0 state. It's only going to be used for oracle purpose. And let's say I first do a CCX on this bit that has been set into 0. So this is C1, C2, and let's say I have C3. And now I do a Toffoli gate with respect to C3 and this Insilia bit that I initialize to 0. And then I do a control X here. And then I do a control X back to reverse this state. So this actually implements this circuit. As you can see, because when C1, C2 are 1, 1, this 1 and 1, it will flip this 0 and make it 1. And if C3 is 1, this 1 and 1 will make this, a -1 flip, because this X will be acted on. And then this, since C1, C2 are already 1, so this 1, 1 will again flip this 0 back, because this 0 becomes to 1 here. And once this, 1 was used to operate on here, then this 1 becomes 0 again. So the 0 goes to 0 at the output, and the state of this minus is changed according to C1, C2, C3. So this is when we implement, because this gate is not available in Qiskit. If you have to implement a 3-qubit, oracle for Groover, you will have to simulate this circuit using this one. Okay. And now I leave it to, work out how you can implement circuits with a hole here or a hole here, because you will have to put an X gates before and after that input. So any question before we go to the implementation? Okay, before I finish, let me, just give you the idea for a general phase oracle. Let's say we have an N-bit oracle. So the idea is actually given in the Nelson Chuang book. So basically it works like this. You have these control bits C1, C2, C3, C4, C5, let's say, and then some bits initialized to 0. And then this is, your target bit. So what you do a Toffoli with respect to the first 2 on this 0th bit, and then a Toffoli with respect to this and this on this one, and then a Toffoli with respect to this and this on this one, and then a Toffoli with respect to this and this on this one. And then you have to flip them back. So you need this one back. So you flip it back. So this basically implements 1, 2, 3, 4 qubit Toffoli gate. For C4X using these Toffoli gates. And of course, these Toffolis are again implemented using different Qiskits. And not only this, actually, you can implement any controlled unitary operation like this. Instead of having an X gate here, if you have an arbitrary U gate using the same logic, you can implement this C and U. All right, so this closes our discussion on oracles, and let me close this one and